That's why I should have an introduction first, right?
Generally, I just jump right into it. Actually, just
Okay, I
quickly.
see.
Yep.
It's the invention of the flash attention. The context window size of the foundation model has been grown significantly. However, there are two main efficiency issues with transformers. The first one is the quadratic training complexity issue, which could be problematic for long sequence modeling. For example, in video generation, the sequence length could be easily go beyond a million level. Also, in DLA modeling, the sequence length could be very large. And in this non-sequence modeling scenario, the attention computation is still a bottleneck. The second efficiency issue lies in the inference complexity. For transformers, it requires to store the KV cache for each token. And so when the generated sequence length becomes larger, the KV cache size becomes larger, and it will eventually incur very high GPU memory burden. Let's have a quick recap of the classical recurrent neural network. ARMs are a very classical architecture that is very popular before the transformers. They have the linear time training complexity. However, this does not mean that ARMs could be trained in a hardware efficient manner. Traditional ARMs, such as LSTMs and the gated recurrent unit, since they involve nonlinear recurrence, their recurrence cannot be parallelized across the sequence length. For inference, the ARMs only need to maintain a fixed state size, so the state size does not grow when the decoded sequence length becomes larger, which is very friendly for long sequence generation. To tackle the training efficiency issue, in recent years, researchers started focusing on a type of iron called the linear iron. By linear, they use the linear recurrence so that their training could be parallelized across the sequence length. We have many types of linear variants. For example, gated linear, state space models, and the linear attention models. In this talk, I will be focusing on linear attention, which is arguably the most hardware efficient one and the most performant one. There is also a significant interest in studying hybrid model. In hybrid model, most layers are linear attention layer, and only a few layers are supermax layers. For example, in a recent architecture called Minimax 01, they use such a hybrid strategy, and 7 out of 8 layers are linear attention layer, and only 1 out of 8 layers are supermax attention layers. Their linear attention layers is a very simple linear attention model with data independent decay, which is called linear lightning attention. We will revisit this later. Next, I'll be introducing some background knowledge for linear attention. First, we have softmax attention. We have its parallel training form and the iterative inference form. The main idea behind linear attention is quite simple. It simply drops the softmax operator from the self-attention mechanism. Then, since everything here is a linear operator, and we can leverage the associativity property of linear operators to rearrange the computation structure. In the end, we have a term called in red, which is the cumulative sum of the outer product between the key and the value vectors in the historical step.
Songlin, can I stop you here? So that S, that's a D by D matrix. And is it true that the rank of that matrix grows with the time step T?
I think in the very beginning, the hidden state is initialized using the zero matrix. So it is like rank zero. And when you have rank one update, its rank is like gradually growing until it reach its maximum rank, like D. Because it is a D by D matrix, so its maximum rank is D.
Cool. And the notation here, you use S sub T just to represent the S matrix at time step T, right? That's not acting as indexing or anything here, right?
Yes. The subscript T is denotes the time step T.
Cool. Okay, thanks.
So linear attention essentially implements animal as linear recurrence, where the linear recurrence is a very simple cumulative sum. And the linear attention has a hidden state ST, which is D by D, a matrix valued hidden state. And this is very different from the traditional arms. For example, in ASTMs, it has only its hidden state size is only in OD, where D is the input dimension. And for linear attention, its hidden state size is in the scale of OD square, which is significantly larger than the case of ASTMs. Since recurrent models relies on the hidden state to memorize the entire historical information, and intuitively, the larger the recurrent hidden state size, the better the memory capacity. And linear attention is essentially use a very hardware efficient mechanism to achieve state expansion. The state expansion is also a frequently noted concept also used in MAMBAR. Next, I'll be discussing how to train linear attention model in a very efficient manner. Previously, we showed linear attention have two equivalent forms, the parallel self-attention style parallel form, and the second one is the recurrent form. For the parallel form, since we have a causal mask here, so we cannot do the matrix multiplications associativity to compute the dot product between key matrix and the value matrix first, which is frequently used in bidirectional linear attention. In the case of causal linear attention, we cannot do it due to the existence of the causal mask M. And in this case, the linear attention's parallel form training total complexity is quadratic in sequenceless, which is still problematic for very long sequence data. Next, we have the recurrent form, which is very efficient in inference, but is not necessarily efficient during the training. Here we can see we have a sequential computation on the hidden state. We have a cumulative sum. This sequential computation will limit the parallelism across the sequenceless dimension. Also, if we look at its update rule, what color in blue is a rank 1 update from the input. And what color in orange is a memory readout. It is a matrix vector multiplication. So both operation is not amenable for GPU tensor core optimization. Tensor cores are very specific computation unit on GPUs that is used for accelerating half precision dense matrix multiplication operations. So typically the minimum size is like a 16 by 16 matrix.
Songlin, can I ask you a quick question here? If this were batch inference, this would be okay, right?
No.
No, still bad?
Yeah.
Can you explain? So if you have batches of V and K, couldn't you make that a matrix multiply, or it would still be inefficient?
I think what you mean is that in like standard transformer inference, you can use the batch dimension to form a matrix multiplication during inference. Say you have an input token, which is of size D-dimensional, and you can use the batch dimension B. We can have a B by D matrix, and we have a previous context, which is say, so we can have a matrix multiplication, right? But in this case, this ST is D by D. So if we have a batch dimension in the beginning, so we have a tensor valued, so it's a tensor value. So we don't have the matrix multiplication there.
I see. Cool. Yeah, I was looking at the blue one, but yeah, that makes sense. One other question I have is just to understand when this is more memory efficient. It's only memory efficient if the length is much bigger than the dimension, right?
Yes.
So like L has to be significantly longer than D for there to be memory savings here, right?
Yes, otherwise, if you maintain the KV cache, it is more memory efficient.
Cool, that makes sense. Thanks.
Since the parallel form and the recurrent form are both load efficient during practical hardware efficient training, and then we have the third form, the trunkwise form. Trunkwise form is essentially a topoloid between the recurrent form and the parallel form. Given a sequence of length L, we have a trunk size C, and we divide the sequence into several equally sized trunk. When trunk size equals to 1, we can recover the recurrent form, and when the trunk size equals to L, we can recover the parallel form. Trunkwise form is not an approximation. Many people ask about this question, like whether this trunkwise form is doing some sort of approximation to the fellow computation. I like to highlight that trunkwise form is not an approximation. It computes the exact same output as both the recurrent form and the parallel form. These three forms are equivalent to each other in terms of the output computation. They just have a different computation structure. So during inference, the recurrent form is more advantage, and for pre-training and training, the trunkwise form would be more advantage. Here we have two key strategy for trunkwise parallel form. So firstly, we compute trunk level hidden state. Firstly, in the recurrent form, we need to compute the recurrent hidden state for each token. But for trunkwise form, we only need to compute a single copy of the hidden state for each trunk. Then after computing all of those trunk level hidden state, we can compute the output based on the input query key and value and the trunk level hidden state. So in this case, we could have a hybrid strategy. And for the historical context, since we already have access to the previous trunk's last hidden states, which encodes the entire historical information, and we can switch to the recurrent form to compute the output contributed from the previous context. And for the local context within the trunk, since we don't have the hidden state, we need to resort to the parallel form to directly compute the output based on the query key and value within this trunk. This is a high-level idea of the trunkwise form. And then before we expand it, I want to have several notation. Here we have a notation to denote the last hidden state of trunk I. Recall that the trunk size is C, and for trunk I, its last hidden state indices is IC. So we use this to denote the last recurrent hidden state for the F trunk. Here we use another notation to denote the query submatrix corresponding to this trunk. So the original query matrix is of size L by D, and in this case, the size is C by D. C is the trunk size, and we extract the submatrix corresponding to the S trunk.
And just understand this notation. The S sub I is going to be the last hidden state, whereas the Q is a range, right? The Q sub I is the range of the whole chunk.
Yeah.
Great.
With these notations, we can formally write down the equation for trunkwise update rule. In the first stage, we only compute the last recurrent hidden state for each trunk here. And what colored in gray here, the intermediate recurrent hidden state, we skip their computation. We do not bother computing their recurrent hidden state. We only compute the last hidden state for each trunk. And this hidden state update could be achieved using like, for example, we need to compute the cumulative sum of the outer product between the keys and the values within this trunk. And in this case, the cumulative sum of outer product could be written in matrix multiplication. This is a wonderful mathematical property for outer product, and it is relatively easy to verify. Here we have the key submatrix, which is of size C by D, and we have the value submatrix, which is also C by D. Now we take its transportation, so we have a D by C matrix, and we take their dot product, so we marginalize over the trunk size dimension C, and resulting in a D by D matrix, which is the same size as the recurrent hidden state. Then we add this to the hidden state to achieve this trunk level state update.
And that last part lets you get it on tensor core because it's a matrix multiply now?
Yeah, here we have a dense matrix multiplication. And a side note is that in order to use tensor core, this C, we need it to be multiple of 16. Because in tensor cores, there are several constraints on the minimum size. We need like 16 to use the tensor core.
And that actually depends on what model of GPU, right? Like the new models have slightly different constraints on that.
Yeah, I think I think for there are some GPU instruction that allow you to the minimal size of matrix multiplication, say M32, 8, and K 16. So the minimal chunk size could be 8 in this scenario. It depends on specific GPU tensor core instruction.
Cool. So we're setting C basically based on the hardware efficiency of the underlying chip.
Yeah. In order to use tensor core, it must be a multiple of 8 or 16, depending on the specific hardware. And also, later I'll introduce there's a fundamental trade-off between the total time complexity and the parallelism. It's better for us to choose intermediate chunk size C to make such a balance.
Cool.
Next, we have output and computation. Let's first focus on the green part, which is called in green. This is the output computation contributed from the historical context. Recall that the historical context is encoded into this recurrent hidden state. That is the last recurrent hidden state of the last trunk. Right? Then for the entire trunk, we can use each token's query to attend to this recurrent hidden state and to retrieve the output from this hidden state. Previously, we have matrix vector product for this memory readout operation. And here, since we have multiple query to read out the same recurrent memory, so we have another dimension, the trunk size dimension, to form this matrix multiplication. And this is why here the memory readout operation is like a batchified operation, and the batch size is like the trunk size. So we can write it into a matrix multiplication. And again, this C should be multiple of 8 and 16, like I explained before. This is for historical context. And the next, we pay attention to what's colored in pink. So for this part, since we do not have access to the intermediate recurrent hidden state, so we have to use the parallel form, that is the self-attention form, to directly compute the output based on the input query key and value vectors. And this looks like exactly the same as a trunk, local trunk attention, except that we do not have the softmax operator here. We do a local trunk linear attention to compute the output contributed by each local trunk context.
And do you have to use tricks like flash attention to avoid making that C by C matrix, or is it small enough that you actually make it in memory?
Yeah, I can also use the flash attention strategy to avoid such a materialization. This is a good point. So it also depends on the trunk size. When the trunk size equals to, like, say, 64, it is small enough to fit into the shell memory. So I can just keep them on the shell memory and directly compute the output. If we use like trunk size equals to 258, which is was used in Mamba 2's actual implementation. They use a trunk size 256. And in this scenario, you cannot just materialize the entire self-attention matrix in the on the shell memory. So in this case, yeah, it's possible to use something like flash attention recomputation strategy and to avoid materialization in this case.
But the right way to think about it is that intra-chunk part is basically, it's going to be computed in a similar way that you would compute standard solid attention.
Yeah. The intra-chunk part is basically exactly the same as like the standard self-attention, except that you have multiple trunks and the effective sequence length becomes the trunk length.
Cool. That's neat.
To summarize, the total complexity of trunkwise form is LOL D square plus LDC. L is the sequence length, D is the high dimension, and C is the trunk size. If we set C to a small number, the overall complexity is linear with respect to the sequence length L. And in practice, we often set C to 64, 128, or 256. The trunkwise form is also a very general algorithm. We can easily extend it to other more expressive variants, such as linear attention with decay or with delta rule, which we will revisit later. Finally, I want to highlight that recent modern linear attention model, such as MS10, GLA, Mamba2, DeltaNet, they all use the trunkwise parallel form for hardware efficient training. Trunkwise form is a hardware-friendly algorithm to train linear attention, but we need some additional optimization on GPUs to retrieve actual workload time speed up. In flash linear attention, we further optimize the I/O cost. For example, the recurrent hidden state, which is called in blue. We keep it on the shared memory throughout the recurrence. And we only load the query key and the value block once and use them to compute multiple terms on S1. Like for this query return, it could be used to compute both the inter-trunk contribution of the output and the intra-trunk, the local contribution to the output. As such, we significantly reduce the I/O cost with the trunkwise linear attention, and this could lead to up to 4 times speed up comparing to the vanilla PyTorch implementation. Flash linear attention is very similar to flash attention in the high-level idea that is to optimize the I/O cost in order to achieve faster workload time running speed.
Songlin, can I ask one more question? When you were talking about it earlier, you mentioned that you thought inference was also slow. Is there ways to apply this chunkwise thing at inference, or in that case, do we just do it one step at a time?
Oh, I think inference is not slow. The recurrent form is not slow in inference.
I see. So they work just standard recurrence is fine for inference.
Yeah, there are 2 stages in the inference phase. The first one is the pre-training. And in pre-training, you can use the trunkwise form. The pre-training is very similar to the training phase, right?
Of course, yeah.
You need parallel computation. In this pre-training stage, people would like to use the trunkwise form for parallel computation. And for the decoding phase, since we can switch back to the recurrent form, in this case, we only need to maintain a fixed-sized recurrent state and then do the recurrent computation step by step, which is very, very efficient.
Cool.
This I/O optimization is only for trunkwise linear attention because, like for inference, for the recurrent mode, we do not need to optimize that much. And for inference, for training, we cannot use the recurrent form for training because it has several limitations, as I described above, previously. Like it cannot be parallelized across the sequence length, and it cannot use the tensor core due to the lack of like matrix multiplication operation. Next, I have some advertisement. I maintained our open source GitHub repo called Flash Linear Attention, where I have a lot of hardware efficient implementation of various modern linear attention models like bright light, GLA based, etc.
Can you speak about whether Triton was sufficient for implementing all of these things? I know I've seen some people say for some tasks you need to go lower level, but for some tasks Triton is fine. How do you feel about that?
I think Triton is a very convenient tool for researchers for fast prototyping their research idea. It is much easier to write than CUDA, and it usually has a relatively satisfactory performance comparing to CUDA. But yeah, because Triton does not have like a very fine-grained memory control on the registers or the shell memory, so it just simply rely on the compiler to do the heavy lifting for you. And this often will not give you the optimal performance. And I think like during for research purpose, it is sufficient to just use Triton to write this model. And for actual production, it's better to write some CUDA code. For example, Hazy Research has a very wonderful library called the Faden Kitten, and they show a significant speed up of the member 2 preferring like trunk-wise kernel comparing to Treedout's member 2's Triton implementation.
So for systems like Minimax, where they implement lightning attention, they're writing that by hand. They're writing the kernels manually.
Yeah, they're writing the CUDA kernel manually.
Cool. I just spoke with the author of Thunderkins yesterday, and I want to write a Thunderkins puzzles. So if anyone has any ideas for how to do that, I thought that would be fun. Cool.
Okay, so to summarize this session, so we introduced linear attention. The concept of linear attention is extremely simple. It's just softmax attention without softmax, and it can be reframed as a linear with matrix value hidden state. We also discussed three equivalent form: the recurrent form, parallel form, and trunk-wise form. The trunk-wise parallel form is more hardware friendly in the training and the pre-training stage. The recurrent form is more preferred in the decoding stage. Finally, we have the flash linear attention, which is the I/O-aware implementation of the trunk-wise parallel form. Next, I'll be discussing linear attention with decay. While linear attention in this form often have a very poor language modeling performance. This one linear attention has been invented back in 2020, but it didn't get much attention because of its poor performance in language modeling. This might be a various reason, and here I provide the most likely reason. So, for example, in language modeling, there is a very strong recency inductive bias. And the recent tokens are often more important than distant tokens in language modeling. So for self-attention, there's a selection mechanism. You can use the softmax to dynamically select the importance of each token. And for many cases, you can see if you like do a visualization of the attention map, the self-attention mechanism values weigh very much on the recent tokens, and also the beginning of the beginning tokens, which is often referred to as the attention sink phenomenon. For linear attention, it is like a bag of word. It's a simple summation, and we do not have any mechanism to weigh more on the recent tokens. This could be a problem. So a very simple fix of this is to have a decay term. Here, gamma is a constant exponential decay factor, where gamma is within the range of 0 to 1. So it is often referred to as the decaying speed. By having a decaying speed, the distant tokens are being forgotten, and the model could weigh more on the recent tokens. And this strategy has been shown very effective in several recent models, such as the RetNet and the lightning attention, which was used in the Minimax 01 model.
Is one way to think of this as kind of just like a running average, like an exponential moving average in the simplest case?
Exactly. It is just a simple exponential, the running EMA mechanism, the running average. And I think there's another model called MEGA, which is explicitly use this running average mechanism, which is kind of the same, but with different name. In the previous case, the gamma is a data independent constant value across different time steps. But in many cases, for different positions, we might want the model to have the flexibility to dynamically control whether to forget the historical information or to memorize the entire history. Here we make this gamma data dependent. By data dependent, it is depend on the input data xt. And so we use like a linear projection to compute this gamma t, just similar to how we compute query key and value in a data dependent manner. As such, this gives the model more flexibility for dynamic control of the memory. And this strategy has been used in many recent models like Mamba-2 and MLSTM. MLSTM is the linear attention module in the XSTM model. They also have a SMSTM module, which is a nonlinear module. Also have gated retention, which is a follow-up work of the Redlight paper. In the Yoko paper, you only cache once. This is also a very interesting paper. And they found like using this gated retention is better than the original Redlight formulation. To train linear attention with decay, we can also have three equivalent forms. And here I briefly introduce the equivalent parallel form for this recurrence. So previously, this D is our quadral mask matrix. Like the lower triangular are all ones, and the upper triangular are zeros. But in
this work, we were calling this M before, but replacing M with D.
This is M before, but here I change it to D because this matrix need to encode the cumulative product of the decay. And now, so for Dij, it requires to encode the cumulative product from the J plus S position up to the S position. So we need to have this. These two forms are equivalent to each other in mathematically. And this also, this duality or the equivalence was referred to as state space duality in the Mamba-2 paper.
Is this the same thing you were using in the first section for the parallel and recurrent or Jog form? Yeah.
It's basically the same idea, except that in this case, we need to incorporate the decaying term into this parallel form. And we can see this is very convenient. We only need to modify the quadral mask. And everything else remains the same. Here we also have the dot product. And once we have this attention matrix, we have another dot product between the value matrix. So incorporating this decay term does not change much about the computation structure. So we can still use the tensor cores, etc., for hardware efficient training. And we can definitely derive equivalent trunk-wise form for this, but I don't have time or space to dive into this, and it's relatively very simple to derive it, and it should be recovering the SSD block decomposition algorithm in the Mamba-2 paper.
Is it fair to say that this strategy is kind of common to a lot of the recent papers where you first derive the duality and then you show how to make one part of it kind of chunk-wise and the other part kind of intra-chunk?
Yes, because recall that for trunk-wise algorithm, the intra-trunk output computation is essentially use this parallel form for computation. So it is very convenient to first derive the recurrent form and then to derive the parallel form. And with these two forms, it is relatively easy to derive the trunkless form, which sits between the recurrent form and the parallel form.
But sometimes the parallel form doesn't look exactly like a tension, right? It can look slightly different.
I think in my I have an intuition that all models that could be written in trunkless form, there's a tension lag parallel form.
Oh, okay, sure. Yeah.
So even for delta lag, there is also a tension lag rule. I briefly mentioned it in the paper.
Cool.
Firstly, we have data dependent decay. This is a scalar value. So for all of these d times d number of channels, they share the decaying speed and gamma t, which could be problematic because in traditional models such as LSTMs, it has more fine-grained control on the recurrent memory. In LSTMs, for each hidden channel, they have a different decaying speed for that channel. So the model could learn. So for some channels, it could have a faster decaying speed to model local context. And for some channels, it could have a very slow decaying speed. So it could better focus on the long-term dependency, right? So inspired by STMs, we can also further enhance this form to a more fine-grained form. Here, this GT is a D by D data-dependent matrix. We can compute it from the input representation like before. However, the increased expressiveness comes with the cost of the computational complexity. In my previous GLA work, I show that only when this GT is written in outer product form, we can write it into a parallel form and correspondingly the trunkless parallel form. We must have a parallel form first and then have the trunkless parallel form. If this GT is not in outer product structure, then we cannot write it in some parallel form that is rich in matrix multiplication. Member one also has a very fine-grained gating matrix, but member one does not have its transition matrix or the gating matrix does not conform to the outer product structure, and this is why member one cannot be trained using trunkless parallel form. It can only be trained using the parallel scan algorithm. And member one cannot use tensor cores at all. And so this brings a significant challenge in further scaling up the recurrent hidden state size. Imagine when you further scale up the recurrent hidden state size, the total number of flops will increase proportionally. And if your model cannot use tensor core for optimization, and these introduced flops will significantly slow down the model. And this is why we want to have the model to have some matrix multiplication operation, so we can use tensor core to optimize these flops in a very effective, efficient manner. And this is why Triddle and Albert they have the follow-up work member 2 in order to scale up the recurrent hidden state size in a more hardware efficient manner. And they have this form. So this form is essentially we can also write it in an auto product form. So the beta equals to gamma t times a 1 vector, and this we can set this alpha t to a 1 vector. And the member 2 conforms to this auto product structure, and this is why member 2 can be trained using trunkless parallel form. In GLA paper, we discussed the most general form. And in practice, we found that for this beta t, we do not need to set it to a learnable vector. We can simply set it to 1 vector, which could boost the training efficiency. And this strategy has been used in many recent models, like gated linear attention and RWKV6.
Can you explain briefly what breaks? There's no duality without this outer product form?
Yeah, I can briefly explain it. I think the reason is just like so say here we have the input, and the input has to be in auto product form because when we have cumulative sum of the auto product form, we can write it in matrix multiplication, and this is kind of similar. For us, this is kind of the similar reason for the gating matrix. We have to parameterize it in the auto product form. So later we can rewrite it into some matrix multiply operations. Auto product has a very, very convenient mathematical structure that allows you to write into matrix multiplication. So this is why we like auto product structure, right? And we can.
You might not know this offhand, but does this change the rank of ST? This multiplication?
Let me see. I think it could be either increased or decreased because here it is not a matrix multiplication; it is element multiplication. So we do not have the so in matrix multiplication, their rank is bounded by the maximum rank of the two matrices, right? But in this case, the element-wise product, then I studied this problem before, and
it could go anyway. So it's not.
So yeah, it could lower the rank or increase the rank. Both are likely. So imagine this GT becomes a zero matrix, and then the rank becomes zero. So you and when this GT is very complicated, it is possible to increase the resulting rank.
I see. Okay, so we're no longer worried about the rank of ST. We're simply worried about being able to get a dual form that's efficient to compute, and you can show that in this way you get that property, right?
Yeah, exactly.
Cool. Yeah, and this feels like a very important idea here, right? It gives you the design space of what we know we can compute.
Yeah, we need to design the model that is friendly to some very common hardware operations like matrix multiplication. Yeah. To have a brief summary, so language modeling has a very strong recency bias, and the linear attention, the varied linear attention does not have such inductive bias. And the decay, which incorporate this inductive bias, would greatly help bridge the popularity gap between linear and supermax attention. Also, fine-grained decay and the D by D gating matrix would improve the performance, but at the cost, it will face some scaling challenges. And the way to go is to make it in auto product form, so we can have the very efficient trunk-wise form for hardware efficient training. Next, the third session, we will be discussing the delta rule. I think I found it convenient to first introduce the concept of fastway programming. So previously we have this memory readout operation, and we can see this is very similar to a linear transformation. If we will this recurrent hidden state ST as a weight matrix, and this the recurrent hidden states of the linear attention amounts to the fast weight. By fast weight, it is a weight matrix that is rapidly changing for each time step. So it is called the fast weight.
And just to be clear for listeners, weight here does not mean parameter of a neural network, right? It means like a kind of activation you're creating that then kind of acts on a different activation, right?
Yeah, I think this fast weight they could be initialized using some actual parameters. So for S0, you can use actual parameters for initialization, and it involves when the model keeps processing the tokens, its weight values will be updating.
Cool. Yeah, but just practically, by the time it's at ST, that's not just like some parameters in the PyTorch sense. That is like an activation.
Yes. It's an intermediate. You can imagine it as an intermediate activation, something like that.
Yeah, just because the terminology is going to get confusing, I want to make sure we're clear.
Yeah. And I think like fast wave programming is a very classical concept in artificial intelligence. So it might be beneficial to get the audience to be familiar with this concept, and it is very convenient to for later discussion.
And then also, when we say classical, today that means like 2020, but you mean like 1970, right? So
Yeah.
actually classical, yeah.
Yeah, it's like ancient, ancient concept.
You have to go that far.
Yeah, so in the framework of fast wave programming, there are two types of weight, the slow weight and the fast weight. So take the linear attention as an example. We have for each input token, we have the query, key, and value projection weight matrix. They are slow weights because they shared across different time steps. Like for each position, you use exactly the same query key and value projection matrix to obtain the query and key values for each position. So they're not changing at all, and so this is why they are called the slow weights. And as explained before, the recurrent hidden state of the linear attention could be imagined as a fast weight matrix. Now the input is the query, and the output is this output. And this fast weight is used to map the input QT to the output OT. So for updated weight, there are many classical learning rules in like the Asian. So in 1960s, there are a bunch of research studying how to update the neural network's weight. For example, the Hebbian update rule, and it directly corresponds to the linear attentions update rule. And there's also a classical learning rule called the data rule. So if we use this data rule to update the fast weight, then we will obtain the data net, which we will revisit later. In the following, I will be explaining both Hebbian and the delta update rule could be regarded as optimizing some online learning objective using test and stochastic gradient descent. Here we have the linear attentions test time objective. It is the lective inner product between the value and the transformed key. We use the recurrent hidden state to do the linear transformation. And this is why firstly we want to introduce the concept of the fast way programming. And from the perspective of fast way programming, it become more later that the memory dot is essentially some sort of linear transformation with fast weight.
Can you explain a little bit where this objective comes from? So like why is this the thing we want to optimize?
I think this is like an ad hoc explanation of the update rule. We have the update rule first, and then we use we from the perspective of gradient descent and to do some explanation for it. I don't think the model is like actually designed to optimize this objective. We are doing some sort of ad hoc explanation for it.
So people found that Hebbian rules worked, and then we go back and try to find the objective that corresponds to, or no?
I think this is not the original motivation.
I see. Okay, so but in a kind of modern sense, your objective seems to say you want to transform your keys so that they're similar to your values, right? And how should I should think of that as like a good transformation matrix that aligns those two aspects? That's roughly what we're saying over time.
I'm sorry, I didn't get your question. So are you saying that why should we have such a objective function? Why should we optimize this? Or
yeah, versus anything else that we might want our asses to be.
yeah, I think so like several days ago I hosted a seminar that there's a test time regression paper, and they unify many recent architectures using the online regression framework. And the common question is that why should we optimize the regression rules at all? And I think from my understanding, in the traditional transformers, there are key value cache out there to use. But in linear attention or other recurrent models, we do not have direct access to the key value cache. However, we still want to have some sort of like information from the previous key value pair. and which is we can also say it like a key value association.
Mm-hmm.
We want the model to memorize the key value association for later prediction, right? This could be useful. And in self-attention, it maintains every key value pair using the KV cache to directly have access to the previous key value association information. But for linear attention, we only have the recurrent hidden state. So we cannot have the direct access to the previous key KV cache. We need to resort to this recurrent hidden state for accessing the previous key value association. And if we have a online learning objective to make the neural network, the linear attention model, to learn to build the key value association of the previous time step, this could be useful.
Cool. So let me just summarize. So standard attention gets access to all the KB cache. We don't have access to all the KB cache. All we have is S. So we want to optimize our S such that it's as close as possible to the other way. And this objective is such that it says, make the keys such that they're easy to access by the current state. And we're kind of compressing the KB cache into S.
Yeah, exactly.
Cool.
So it's like a associative memory explanation. And linear.
Well, we don't even need those terms. We can just say we're trying to make it as close as possible, right?
Yeah, definitely. And for linear attention, we have a very simple objective. This is just a first order inner product between the transport key and the value. Like we said before, we want to do some sort of regression to recover the value based on the key, right? And this loss function. So if we have this objective, and if we minimize the selective inner product, or equivalently, we maximize their inner product. And there are two ways to do so. Firstly, we can minimize the angle difference between the transport key and value. And the second thing to do is to the model does nothing but increasing the norm of this norm the hidden state matrix, and then their inner product could also be enlarged, right? Because of this, the linear attention could often encounter some numerical instability issue. For member 2, it uses a decay term in the weight matrix. And from the perspective of gradient descent, this decay term is like weight decay, which is a very classical concept in like SGD. So we often use like SGD ADEN with weight decay. And this is in a similar way.
By having saying like they have an L2 regularizer on that.
Yeah. You can also write it, rewrite this objective and U plus L2 normalization on the norm of the recurrent hidden state, and it will give you the weight decay term. On the other hand, for DataNet, it directly optimizes the Euclidean distance between the transport key and the value. So if the model learns a very large recurrent hidden state norm, and the resulting transport key would have a very large norm, right? And their Euclidean distance or L2 distance will be very large. And the model want to do some to minimize their L2 distance, so the model won't want to simply increase the norm as the previous case. So in this sense, the data-less objective make it more numerical stable. Because once this ST, the norm of ST is like out of control, it will have a large penalty for it. Also, personally want to build the key value association, and this regression rules is better to do so.
Are there any downsides, or is this strictly better?
I think if we care about like linear regression, I think this L2 loss is definitely better than this first order inner product loss. Yeah, strictly better. I don't foresee many downside of it, but I think like in classical machine learning, there are some like risk of overfitting, but we want to overfit anyway. In this case, we want to memorize the first key value association. So I don't think that would be a problem in this case.
Actually, this did come up slightly in the other talk where he was saying that it's not just that you want to memorize, but you also want it to be in a good place to take in new keys as well. And so there is an overfitting problem where if you get a new input that's very different than the other inputs, it actually might be a problem. But that's maybe future work to figure that out. Yeah.
Yeah. Next, we have a in-context associative record task and the MQAR task, which is very popular to test subquadratic models. The MQL task is very simple. So in the previous context, there are a bunch of capital letter and number association provided in the previous context. And then the model is asked to reconstruct the number associated with each capital number. Self-attention could do a perfect job in this case, but for linear model, they suffer from this very simple task when the model dimension is slow. So when the model dimension is slow, their recurrent hidden size is small, and they can't just use the recurrent hidden memory to memorize all of the historical information. The model is required to have a better updated rule strategy to memorize those patterns. And for data led, because it has a better update mechanism, so and it directly minimizes the key value association prediction, and then no wonder data led could have very, very good performance, even when the model dimension is very small.
So to get this right, you almost have to have 64 orthogonal dimensions in your S. You're basically fully using your dimensions in this case. Is that fair?
Yeah. Kind of. Yeah, I won't say DLL is can solve an arbitrary MQL problem. It depends on the model dimension. Because in this case we have 64 key value pairs, and ideally all the model should be able to memorize all of the key value pairs using a 64 model dimension.
Right.
But other model cannot do it because they don't have a good strategy to store this key value pair into the memory. And for data led, it has a very good strategy to do so.
And the theory of the case is that from a regression standpoint, each of these other methods was like too far away from the ideal likelihood. Okay, cool.
Yeah, kind of. Next, I'll be discussing the expressiveness of the data net. And here we have a complexity on class. And the disclaimer, I'm not a theory people, so I might not fully understand what TC0 or NC1 is. But transformers and members are within the class of TC0, according to this wonderful paper by Will Merriam and the illusion of state in state space model. They showed that for linear RNN with diagonal transition matrix, for example, in the case of GLA, for all this sort of model, their effectiveness is within the class of TC0. And for many more complex tasks, for example, playing the chess, coding, and do some entity tracking, it requires the model to have the expressiveness of like in the NC1 class to solve this problem. And a side note is that so for transformers, we can use chain of thought to make it able to solve NC1 problem. But I was wondering, like, whether we can design a really more expressive model from the first principle. So if a model in the very beginning, it can have achieved the expressiveness of NC1. So we might not need to have the chain of thought to do this sort of to solve this complex task.
So the theory is that models like DeltaNet potentially have more expressivity than both kind of models like Mamba and models like transformers.
Yes.
Cool.
And in their paper, they show that in order to make our model to be able to go beyond the TC0, there are two strategies to do it. The first strategy is to make it nonlinear, and just like STMs and gated recurrent unit. But this strategy is definitely break down the parallelism, and it will be very hard to train in practice. Luckily, they also provide a second strategy, that is we can still use the linear iron, but we need to make the transition matrix more expressive. We need to make this transition matrix data-dependent, non-diagonal transition matrix. If the transition matrix is not data-dependent, we could do some sort of like a diagonalization for all of this matrix because they are simultaneously diagonalizable, and we can always do the diagonalization, just like in the case of S4. In S4 we have the dense matrix, and we do the diagonalization for each 10 step simultaneously, and so we can have the equivalent S4D. So this is why we have S4D. This
Well, maybe we'll have Ankit and Meryl on later to talk, but this is great for now. Cool.
Yeah.
So clear.
And if we rearrange the computation of the data length update rule, we can rewrite it into a linear recurrence way. And here we have the transition matrix, and here we have the input. The transition matrix is a generalized household transition matrix. Why I call it a household matrix? Because when this beta t is set to 2, it is just a classical household transform when this key is L2 normalized. And this is why, since we relax the range of this beta t, so I call it a generalized household transition matrix.
And just to understand, does this matrix fit the conditions earlier, or the G conditions that it has to be an outer product, or no?
I think yeah. So here we have the auto product again, and we'll show it later. This is very convenient for a very efficient matrix verification operation. Just like in the case of GLA, we make the gating or the decaying matrix to be in auto product form. And in this case, I think it is in a similar way, and this auto product structure could help a lot in later computation. And this transition matrix is data dependent because the keys are data dependent. This is of the form of identity minus low rank. So your level will be a diagonal. It could be diagonal matrix, but as long this kt does not equal to 0 vector, it is no longer a diagonal matrix. So for data let it satisfies the necessary condition for our model to be able to for its expressiveness to be able to go beyond TC0. And next, I have some very quick proof of data is actually its expression is indeed beyond TC0. So if we unroll this recurrence, we will have a cumulative product of this generalized household transition matrix product. And in a very, and in a recent ICLEL 25 paper, notably this paper has been selected as an oral paper. In this paper, they show that the cumulative product of this generalized household matrix can represent any matrix of norm smaller than 1. So to represent any other matrix, you only need to like scale it up to constant. So this form could like mimic or to approximate any other real matrix. And there is a classical conclusion from the complexity theory is that the cumulative product of general matrix cannot be computed in TC0 time. So this is why data light with negative eigenvalue has expressiveness beyond TC0. Yeah, I discussed it with several folks, and we come up with this conclusion.
Cool.
Here we have some state tracking task, which is requires the model to have experience beyond TC0 or even beyond NC1 to solve this problem. The first simple synthetic task is the parity track. Essentially, it requires the model to track, given the model a 0, 1 serial string, and the model to count whether the string has an even number of 1 or an odd number of 1. This task is very simple, but for transformers, transformers will have a zero performance in this very simple task because transformers effectiveness is limited within the class of TC0. And for SSTM, it's a nonlinear iron. Then it could resolve this synthetic task very easily. Recall that there are two conditions to go beyond TC0 for our model. The first condition is to make it nonlinear, and the SSTM is indeed a nonlinear iron model, so it has a very good performance in this parity tracking problem. In this Eclair paper, they found that if we relax the range of the eigenvalue from 0 to 1 to -1 to 1, then the state tracking performance could be boosted for both Mamba and delta light. And I can also imagine for other linear recurrent model. As discussed before, delta light has strictly more expressive power than Mamba. And then for those harder tasks like modular arithmetic task, delta light with negative eigenvalue greatly outperform Mamba with negative eigenvalue. This is because.
Can you explain briefly what negative eigenvalues give you here? Is it like periodicity, or what does it provide?
I think sort of to my intuitive understanding. So if you do state tracking task, and I think like the positive eigenvalue is like doing the addition, and the negative eigenvalue is like doing the subtraction.
Okay.
You need both positive eigenvalue and negative eigenvalue in order to do this parity checking task, right?
Cool. Okay, I think we could maybe move on to the next part. This is really neat, but I think maybe beyond our understanding. Yeah, you're going to talk about how to make it efficient.
Yeah, this is what I am good at.
Cool. Yeah, well, let's talk about that. Yeah.
I'm good at making efficient. Whenever you want to parallelize iron training, you need to unroll this recurrence. By unrolling this recurrence, you will have some cumulative product of the transition matrix. If we use an arbitrary unstructured dense transition matrix AT here, then we would have a cumulative product of arbitrary unstructured matrix, so the matrix multiplication complexity for two D by D matrix is D to the cubic, right? And this could be very, very expensive because we are doing cumulative matrix multiply here. And this could, so if this transition matrix is not structured, and this cumulative product could be of the complexity L D to the cubic, so it is totally unacceptable. But luckily, for the delta light case, we have a structured transition matrix. This is identity plus low rank structure, and this is very, very convenient to achieve this cumulative product. And actually, this problem has been well studied in the numerical linear algebra literature. So like I said before, this transition matrix is generalized household matrix. And the cumulative product of household matrix has been well studied because cumulative product of household matrix has many applications. Like imagine if you call PyTorch QR decomposition, the PyTorch will secretly call cumulative product of household matrix a subroutine to solve the QR decomposition. And this cumulative product of household matrix is extremely important in numerical linear algebra, and it is well studied. And here I stand in the I use their very amazing algorithm called the WY representation. So this is a very classical algorithm to compute the cumulative product of the household matrix in a very memory and computation and efficient manner.
Where did the beta go? Does this go away?
This one?
The inner beta, yeah.
I think the household I think I only need to do some small adaptation to the WY representation.
Yeah, it's W inside it.
Yeah, I can do some generalization. So I can these two vector do not need to be the same. I can make some even some more to make it more flexible. So for example, I can make this matrix diagonal matrix and these two vectors to be different from each other. And I can still have a algorithm that inspired by this WY representation.
Oh, cool. So you're showing the general form of the WI.
Yeah, kind of. And I only present the key intuition of the W representation. So here we have the cumulative product of the transition matrix, which is difficult to handle. But with WY representation, you can write it into the identity matrix minus the cumulative sum of the outer product of two vectors. Cool. And we have encountered this before, right? In linear case. So okay, this is our old friend, and the cumulative sum of the outer product. We can write it into matrix multiplication in the following, which is very hardware efficient. And unfortunately, I do not have additional slides here to explain this amazing, very wonderful algorithm in detail. But I want to highlight that. So I can briefly explain it because so firstly, we do not have this cumulative product of the transition matrix. So what's colored in green? So firstly, it's like identity matrix in the vanilla linear attention trunk case, and in this case, we need to compute the cumulative product of the transition matrix within this trunk, and this cumulative product could be written in this form. And then we have this auto product structure, and you can you don't know where this W and K come from.
Right.
Just like stack them into a matrix and do batchified matrix multiplication. Yeah, it's very similar to the linear attention case, and this auto product structure is extremely useful.
Cool. Oh, great. Yeah, I get the strategy. You're making an outer product that you can group them together in the chunk. And,
yeah, and this is the main idea behind this strong-wise algorithm. And I think I don't need to dive into details. And I have a blog post to explain this in very, very detail. And
can you explain briefly the bottom part? So the bottom part, it still looks like QKM, just like standard attention, but the values now are slightly different. Is that right?
Yeah, there is a concept called pseudo value from the original data paper, and I follow them to use this concept. But I think in my paper, I show that there is a form that is more similar to the self-attention style. So I don't need to modify the value at all. I can directly modify the way to compute the self-attention matrix in matrix multiplication.
But kind of high level, once you've done this mathematical transformation, you can basically plug this roughly into the linear attention you had previously and get a kind of similar form of the algorithm.
Yes.
Cool. Yeah. So it's all still tried in. It's all pretty fast in that way.
Yeah. So whenever we have the pseudo value here, and actually we can call the previous linear attention kernel to compute.
Oh, exactly. Okay. Cool.
Yeah. So this is convenient in computation. So we write it in this form. But we could also have a more self-attention, like attention style computation. Yeah, I briefly explain it in the paper.
Cool.
And next, I'll be introducing two recent follow-up of the data-led work. The first one is by myself. This paper had been published at ICLEL 2025. And the idea is extremely simple. I just combine Mamba 2 gating with data rule. So make them to be as a whole, as a single transition matrix in a single layer. As a result, so the gated data light has consistently better performance than either Mamba 2 and the data light in all the tasks have been evaluated. And I refer readers to my paper for more details. And recently, there's a archive paper like in several days ago, and it called Data Product. And essentially, so previously we showed that so data lab is optimizing the online linear regression rules using a single step of test time stochastic gradient descent. And so why not we optimize do several steps of SGD in a single time step? So this is sort of like a test time scaling. We can do multiple gradient descent step in a single step. We can yes, so to minimize that function. And in this paper, they indeed do such a strategy, and I read the resulting form. I think it's more informed because we can see here the transition matrix is now not a rank 1 update matrix. It is a rank NH. NH is the total number of product they use. It is a high rank update, so which could greatly improve the expressiveness. So although previously we showed that the data light is beyond TC0, but in order to approximate arbitrary matrix in a single step, we need d number of household matrix multiply to approximate arbitrary dense matrix. And in their paper, they show that in a synthetic task S4, they show that by simply increasing the rank from 1 to 2 and 3, it could boost the performance in this task. And they also do some other experiment like in this is code modeling, and they found I think in code modeling this task is like very related to state tracking, because in code there are a lot of like variable tracking and stuff like that. It is requires the model to have more state tracking ability, and they show that this model has better performance in this coding task.
Two quick questions. Is the rank is linear with the number of gradient steps? Is that right?
Yeah.
Cool. And the amount of flops is also linear in?
Yeah. Yeah.
And then final question. Do they think about how to do inference with this model? Can you do like chunks of 8? Since you have fast ways of doing those chunks, can you basically do that at inference time?
Yeah, I think previously in the recurrent stage, we do not need to use like trunkwise form, but in their stage, they could leverage the trunkwise form for each time step, because they have multiple this sort of update in a single step. And once, let's say this update, if they have like a 16 update in a single step, then essentially we have another trunk size 16 for us to do matrix modification.
Right, and it's basically free for GPUs at inference time, right? Yeah, it's pretty cool.
And I found this to be very promising. We can increase the data length rank. I'm wondering if we increase it to like D is the model dimension, then and data like could approximate arbitrary dense matrix in a single step.
Right. I guess you still have the problem that you are limited by the dimension size, but the dimension size is pretty big, right? Yeah.
Yeah.
That's really interesting. Cool.
And to have a brief summary, we discuss the linear attention and the data light from the perspective of fastway programming and the test time stochastic gradient descent. Data light has really more expressive power than at Mamba or GLA, while maintaining the ability to be trained in parallel. And some recent follow-up show that the gating mechanism and some high rank update could further boost the performance of data light. So they are, so it looks very promising to me. Okay, next I'll be I'm presenting the last session, finally, the beyond linear regression objective. Recall that data light optimize online linear regression laws. However, this assumes that the historical data is linearly dependent to each other. But in generative AI task, like language modeling, it involves highly nonlinear dependency between the data. So optimizing these linear regression nodes might be suboptimal. So very literally, in the test and training, short for TTT, in TT layer, they optimize the nonlinear regression laws. So here, we are not using a linear transformation as for the linear transformation. Instead, we use a nonlinear transformation, which is parameterized by the hidden state S. So for example, they have TTT linear and the TTT MLP. In TTT linear, they have the same linear projection, but they have the layer law operation here to make the entire model nonlinear. In TTT MLP, they use S to parameterize a MLP layer.
So the thing you're passing around, the like RNN hidden state, is now the kind of parameters of a neural network, right?
Yeah.
Cool.
Yeah, so this is why I introduced fast-wave programming in the very beginning.
Oh, I see it in that sense, yeah.
Yeah, because I found it more convenient to understand this why we should use the recurrent hidden state to be the parameter of another neural network. This is like a hyper network or fast-wave programming.
Yeah. It's like you have to get a little bit meta, right? It's like a network embedded in the network, right? Yeah.
Transform in transform or stuff like that. I think we have a bunch of these concepts and yeah.
That's always confusing. I don't know. I'm always confused, but okay, cool. So now you have S you're passing around as the way to a neural network. Cool.
Yeah, so they have a nonlinear regression loss, which is cool, but at what cost? If they induce their recurrence using gradient descent, and since there are nonlinear loss out there, and the resulting recurrence would be nonlinear. And we all know that for ours, nonlinear cannot be parallelized across the sequence length, which is a sad story. We have it more expressively, but we cannot parallelize it across the sequence length. To solve this problem in TTT, they come up with a strategy called mini batch gradient descent. So in TTT framework, each token is treated as a training example, and the model is keep doing gradient descent using the training data, which is the input token. And by mini batch gradient descent, they do a single parameter update by training on several training example or processing several tokens in this case. So the mini batch size aligns with the trunk size in the context of sequence modeling. And the token within the trunk is treated as independent training example. So we can use the same weight for parallel processing. This is just like a batchified neural level training. It's very classical. However, so if we simply do this, the token within the trunk is orderless. So we don't have the order information for the tokens within the trunk. So
can I understand exactly what this means? It means that let's say there's I don't know 64 tokens in a chunk. All of them use the same starting RNN state. Is that right? I see. Okay, so that's what you mean by you've lost the order in the chunk.
Yeah. They use the same recurrent the weight matrix or the fast weight matrix or the last chance last hidden state. Also, they're equivalent to each other. So they are orderless in parent, but for sequence modeling, we are doing autoregression modeling. So we need to maintain the causal dependency. In order to solve this, they introduce a very lightweight linear recurrence in the trunk. So it is just like a simple cumulative sum of the gradient in this trunk. So they have a secret hidden state running when processing.
I see. So it's nonlinear between chunks, and within the chunk, it's just linear. Okay.
Yeah, so this is why I refer to their strategy as intra-trunk linear and inter-trunk nonlinear. Yeah.
Cool.
And then for Titans, which is a very recent, very popular paper, and they are essentially based on the test and training paper. Is that they use exactly the same training online learning objective, that is the nonlinear regression rules, and they use the same parameterization. They also have Titans linear, Titans MLP, stuff like that. The only change to the pure RNN layer, I know like Titans have another like hybrid model architecture, but for the RNN architecture, there are many difference lies in the introduction of the momentum term and the weight decay terms. So in
TDT, we're inventing deep learning optimization, but now inside of the RNN, right?
Yeah. So in TDT or data light, it just is the very low stochastic gradient descent. And in Mamba 2 and the gated data light, the gating mechanism could be imagined as a weight decay term. And in Titans, they not only use the weight decay term, but also the momentum term to optimize this nonlinear objective. So I think like the momentum term and the weight decay term, both of them are very classical in like stochastic gradient descent. And I found this concept very promising. So you can bring many recent advances in optimizer.
So maybe the question is like, why haven't we seen TTT Atom W yet? Or
yeah, we can also have TTT solve, TTT.
just so right. Okay, well, it's good. We need papers to write. Yeah.
Yeah. We are pointing out some way to make papers.
Cool.
And finally, to summarize, in this talk, I frame many modern linear attention model in the framework of like online learning. So these models are doing test time stochastic gradient descent on a online learning objective. So for decaying gated or gated linear attention, they optimize the various live elective interpol dollars. For data light and gated data light, they are optimizing the linear regression loss, and for TDT and Titans, they're optimizing the nonlinear regression loss. Aside from the learning objective, so the optimization is also crucial, and there are many techniques for gradient descent optimization, like weight decay and the momentum. It could be interesting to see if there are any other gradient optimization technique to be used in iron update. To achieve efficient training, we must have some sort of trunkwise form. In linear attention, the trunkwise form is an exact form. But for TTT and Titans, like we explained before, it is a hybrid form, but it's still in some sort of like trunkwise computation. Here the trunk is like a mini batch gradient descent, and they process all of the tokens within this trunk in parallel. And they also have a minimal lightweight linear recurrence to build the cultural collection. So this is the so-called hybrid inter-trunk nonlinear and intra-trunk linear recurrence. And in the future work, it is very interesting to derive different learning objectives using different optimizer to guide the design of architecture. Yes, thank you for this.
Thank you. Yeah, this is wonderful.